This is day 16 of Advent of Cyber 2023, and this challenge is called Can't CAPTCHA This Machine. McGreedy has locked McSkitty out of his ELF trademarked H-Quarters admin panel by changing the password. To make it harder for McSkitty to perform a hackback, McGreedy has altered the admin panel login so that it uses a CAPTCHA to prevent automated attacks. A CAPTCHA is a small test like providing the numbers in an image that needs to be performed to ensure that you are human. This means McSkitty can't perform a brute force attack, or does it? After the great success of using machine learning to detect defective toys and phishing emails, McSkitty is looking to you to help him build a custom brute force script that will make use of machine learning to solve the CAPTCHA and continue with the brute force attack. There is, however, a bit of irony in having a machine solve a challenge specifically designed to tell humans apart from the computers. So the learning objectives, we're going to learn about complex neural network structures, how does a convolutional neural network function, using neural networks for optical character recognition, and integrating neural networks into red team tooling. So for this challenge, the only thing we will need to do is start the machine. Okay, introduction. In today's tasks, we'll get our first look at how red teams can use machine learning to help them attack systems. But before we can start attacking the admin portal, you'll need to expand on some of the ML concepts taught in the previous tasks. Let's dive in. Convolutional neural networks. In the previous tasks, we talked about neural network structures. However, most of the structures were fairly basic in nature. Today we'll cover an interesting structure called a convolutional neural network. CNNs are incredible ML structures that have the ability to extract features that can be used to train a neural network. In the previous task, we used the garbage in, garbage out principle to explain the importance of our inputs having good features. This ensures that the output from the neural network is accurate. But what if we could actually have the neural network select the important features itself? This is where CNN comes into play. In essence, CNNs are normal neural networks that simply have the feature extraction process as part of the network itself. This time, we're not just using maths but combining it with linear algebra. Again, we won't dive too deep in the maths to keep it simple. So the three main components of CNN is feature extraction, fully connected layers, and classification. We've actually already covered the last two components in the previous task, a simple neural network structure, so our main focus for today will be on the feature extraction component. So feature extraction, CNNs are often used to classify images, or we can use them with almost any data type. Images are the simplest for explaining how a CNN works. This is the CAPTCHA that we are trying to crack. Since we'll be using a CNN to crack the CAPTCHA, let's use a single letter in the CAPTCHA as our image. So using a 4. Image representation. The first question to answer is how does a CNN actually perceive this image? The simplest way for a computer to perceive an image is as a 2D array of pixels. A pixel is the smallest area that can be measured in an image. Together, these pixels are what create the image. A pixel's value describes the color that you are seeing. There are two popular formats for pixel values. So RGB, the pixel is represented by 3 numbers from 0 to 2255. These 3 numbers describe the intensity of the red, blue, and green colors of the pixel. And there's also grayscale. The pixel is represented by a single number from 0 to 255, where 0 means fully black, while 255 is fully white. Any value in between is a shade of gray. To represent the image as a 2D array, we start at the top left and capture the value of each pixel, working our way through to the right in rows before moving down. So this GIF describes how it works. So you start off with an image, grabs the image, breaks it down into smaller chunks, then the small chunks turned into a 2D array, and then the values within those cells are looked at. Convolution. There are 2 steps in the CNN feature extraction process that are performed as many times as needed. The first step is convolution. The maths is about to get slightly hectic here, so take a deep breath and let's dive in. During the convolution step of the CNN's feature extraction, we want to reduce the size of the input. Images often have several thousand pixels, and while we can train a neural network to consider all of these pixels, it will be incredibly slow without really adding any additional accuracy. Therefore, we perform the convolution to summarize the image. To do this, we move a kernel matrix across the entire image, calculating the summary. The kernel matrix is a smaller 2D array that tells us where the image we are currently creating our summary. The kernel slides across the head and width of the image to create a summary image. So this animation, we've got this larger 6x6 and it turns it into a 4x4. As you can see from the animation, we start at the top left of the image at a smaller 3x3 section. We then calculate the summary by multiplying each pixel with the value in the kernel. These kernel values can be set differently for different feature extractions, and we're not limited to a single run. The values of these kernels are usually randomized at the start and then updated as the network is busy training. We say that each kernel run will create a summary slice. As you can see from the animation, by sliding this kernel across the entire image, we can create a smaller summary slice of our image. There are a couple of reasons why we want to do this. As mentioned before, we can create a neural network that takes each pixel's input, but this would be an incredibly large network. with improved accuracy, the summary created by the convolution process still allows us to capture the image's important details without needing all the pixels. If our CNN's accuracy decreases, then we can simply make the kernel smaller to capture more details during the input phase. The term used for this process is sparse interaction, as the final neural network won't directly interact with each pixel. If you want to learn more about it, you can read in this link here. If we calculate a feature in one location in our image, then that feature should be just as useful as a feature calculated in another location of the image. Making use of the same kernel to determine the summary slice means that this condition is met. If we update the weights in one of our kernels, it will alter the summary for all pixels. This results in something called the property of equivalence to translation. Simply put, if we change the input in a specific way, the output will also get changed in the same way. Pooling. The second step performed in the CNN feature extraction process is pooling. Similar to convolution, the pooling step aims to further summarize the data using a statistical method. Let's take another look at our single slice and how our max pooling will provide a summary of the maximum values. So it's got the 2x2 grids in here and it grabs the highest value. So it's E0, E9, 98, F9. As you can see again, for each kernel we create a summary based on the statistical method. For max pooling, this is finding the maximum value in the pixels. We could also use a different statistical method such as average pooling. This calculates the average value of the pixels. And that is basically it. That's how the CNN determines its own features. Depending on the network structure, this process of convolution and pooling can be repeated multiple times. In the end, we're left with the pooled values of each of our slices. These values now become the inputs for our neural network. So, fully connected layers. Now that we have our features, the next stage is really very similar to the basic neural network structure that we are used back in the introduction to machine learning task. Create a simple neural network that takes inputs, run them from the hidden layers, and then finally provide an output. This is called the fully connected layers portion of the CNN, and this is the part of the neural network where each node is reconnected to all the other nodes in the layer. Classification. Lastly, we need to talk about the classification portion of the CNN. This is the output layer from the fully connected layers portion. In the previous tasks, our neural networks only had one output to determine whether or not a toy was defective or whether or not an email was a phishing email. However, to crack CAPTCHAs, a simple binary output won't do, as we need the network to tell us what the character is. Therefore, we'll need an output node for each potential character. Our CAPTCHA example only contains numbers, not letters, so we need an output node from 0 to 9, totaling 10 output nodes. Having multiple output nodes creates a new interesting feature for our neural network. Instead of simply getting one answer now, all 26 outputs will have a value decimal between 0 and 1. We'll then summarize this by taking the highest value as the answer from the network. However, nothing is to stop us from reviewing the top 5 answers, for instance. This can help us identify areas where our neural network might be having issues. For example, there could be a little confusion between the characters of M and N, as they are very similar. Reviewing the output from the top 5 nodes will show us that this might be a problem. While we may not be able to solve this confusion directly, we could also use this to our advantage and increase our brute force accuracy. We can do this by simply discarding the CAPTCHA if it has an M or N, and requesting another to avoid the problem entirely. So training our CNN? Now that we've covered the basics, let's take a look at what will be required to train and use our CNN to crack the CAPTCHAs. Please note that the following steps have already been performed for you. The next steps will be performed in the hosting the model section. However, understanding how training works is an important aspect, so please follow along and attempt the commands given. So we'll be making use of the tension OCR for our CNN model. CNN structure has a lot more going on, such as LSTMs and sliding windows, but we won't dive deeper into these steps in this instance. The only thing to note is that we have a sliding window, which allows us to read one character at a time, instead of having to solve the entire CAPTCHA in one go. We'll be making use of the same steps following to create CAPTCHA 22, which is a Python pip package that can be used to host a CAPTCHA cracking server. If you're interested in understanding how this works, you can have a read here. While you can try to run all the software yourself, most of the ML component runs on a very specific version of TensorFlow. Therefore, making use of the VM attached to the task is recommended. So to crack CAPTCHAs, we have to go through the following steps. Gather CAPTCHAs so we can create labeled data, label the CAPTCHAs to use in a supervised learning model, train our CAPTCHA cracking CNN, verify and test our CAPTCHA cracking CNN, export and host the trained model so we can feed it CAPTCHAs to solve, create and execute a brute force script that will receive the CAPTCHA, pass it on to be solved, and then run the brute force attack. Steps 1 to 4 are quite taxing, so they have already been completed for you. We'll do a quick recap of what these steps involve before moving on to hosting the model and cracking some CAPTCHAs. To do this, you have to start the Docker container in a terminal window. So I've got the VM open, but it's not opened here yet, so I'll go up here, show split view, then I'll move it into a separate window. Okay, so open up the terminal. Okay, then the command it wanted us to run was this, so we'll just copy that, paste it in this section, and we'll paste in here. So it's a Docker command that we are running, and I assume that created a container for us. Yeah, so we've got this container here that is running, so just clear that terminal. This will start a Docker container that has TensorFlow and AOCR already installed for you. You'll need to connect to this container for the next few steps. First, you'll need to find the Docker containers ID using the following command. So docker ps, so double click, then copy. Then we need to enter into the container with the command docker exec-ti container, then bash, and we are now inside the Docker container. So cd into the OCR directory, so cd/OCR, and we are now in that directory. In order to train or capture cracking CNN, we first have to create a dataset that can be used for training. Let's take a look at the authentication portal for HQ admin. So we'll go to this address and we will open it in the web browser, and it already took us to there. So you'll see the following authentication page has username and password and a place to enter the captcha. So as we can see, the authentication portal embeds a captcha image. We can get the raw image using a simple curl command. So we can do that in here. So that whips out in curl. Actually, that might need to be in the output. You'll see a base 64 encoded version of the captcha image. We can write a script that will download the image and then prompt us to provide the answer for the captcha to store in the training set. This has already been done for you, so you can view the stored data using the following command. So that'll be ls-alh, then the directory raw dataset, raw data dataset. Creating the training dataset. Next, we need to create the training dataset in a format that AOCR can use. This requires us to create a simple text file that lists the path for each captcha and the correct answer. A script was used to create this text file and can be found under the labeling directory. You can use the following command to view the text that was created, so cat labels training. So as we can see, when we ran the previous command, we've got all these images in here, and there's a script as well. So now once this cat labels, was it cat training labels? No, labels training.txt. So it's got all that there. Once we have our text file, it has been converted into a TensorFlow record that can be used for training. This has already been done for you, but you can use the following command to create the dataset. So we will copy this and put it into the virtual machine, and inside here we will paste it. So AOCR dataset training, then TF records. So run that, and we'll come back to it when it's done. As mentioned before, this has already been done for you and is stored in the labels directory, so we didn't actually have to run that. We've created two datasets, one for training and one for testing. As mentioned in the introduction to machine learning task, we need fresh data that our CNN has never seen before to test and verify that the model has been trained accurately, not overtrained, just as in the previous task. We'll only use the training dataset to train the model, and then the testing dataset to test its accuracy. So training and testing the CNN. Finally, we can start training our model. This has already been done for you, but with all the preparation completed, you would be able to use the command to start the training. It turns out that previous command we were running didn't work, so we'll just clear. And then this was also done for us apparently. So training will now begin. Once the training is completed, a couple of steps. Stop it by pressing Ctrl C. Let's take a look at one of the output lines from running the command. I guess maybe we should be running this one. So we'll just paste that into here and do that. So let it run a little bit. So training now begin. Once the training is completed, a couple of steps, stop it. Then take a look at the output lines. Okay, so it's on that. Starting the training process now. Or just leave it for a little bit and see what it does. Okay, so we've seen it run a few steps, so we can Control C to stop that. I need to press a few times to force it to stop. There we go, so we can see what's doing. So in each of these steps, the CNN is trained on all of our inputs, similar to what was discussed in the introduction to machine learning task. Each image is given as an input to the CNN, which will then make a prediction on the numbers that are present in the captcha. We then provide feedback to the CNN on how accurate its predictions are. This process is performed for each image in our training dataset. To complete one step of the training, the output from AOCR shows us how long it took to perform this round of training and provides feedback on the loss and perplexity values. So loss is the CNN's prediction error. The closer the value is to 0, the smaller our prediction error is. If you were to start training from scratch, the loss value would be incredibly high for the first couple of rounds until the network is trained. Any loss value below 0.005 will show that the network has either completed its learning process or has overtrained on the dataset. Perplexity. This refers to how uncertain the CNN is in its prediction. The closer the value to 1, the more certain the CNN is that its prediction is correct. Consider how perplexed the CNN would be seeing the image for the first time. Seeing something new would be perplexing, but as the network becomes more familiar with the images, it's almost as if you can't show it anything new. Any value below 1.005 would be considered a trained or overtrained CNN. So as it's already trained, we can run the test on it. Let's go to here, paste into there. Let's clear the terminal and then run the test. So let that run. So testing will now begin. Once a couple of testing steps are complete, you can stop it with Control C again, and you'd see this as the output. So yep, as you can see here, quickly Control C to stop it. Getting 99% accuracy for most of them. So as you can see from the testing time, running a single image sample through the CNN is significantly faster than training it on the entire dataset. This is one of the true advantages of neural networks. Once training has been completed, the network is usually quick to provide a prediction. As you can see from the predictions provided at the end of the lines, one of the CAPTCHA predictions was completely correct, whereas another was a prediction error, mistaking a 5 for a 6. If you compare the loss and perplexity values of the two samples, you'll see that the CNN is uncertain about its answer. We can actually use this to our advantage when performing live predictions. We can create a discrepancy between CAPTCHA prediction accuracy and submission accuracy by not submitting the CAPTCHAs that we are too uncertain about. Instead, we can create a new CAPTCHA. This enables us to change the OPSEC of our attack, as the logs won't show a significant amount of entries for incorrect CAPTCHA submissions. We could even take this a step further and save the CAPTCHA images that were incorrect on submission. We can then label these manually and retrain our CNN to further improve its accuracy. This way, we can train a super CAPTCHA cracking engine. You can read more about it at this link. So, hosting our CNN model. Now that we've trained our CNN, we'll need to host a CNN model to send it CAPTCHAs through our brute forcing script. For this, we'll use TensorFlow serving. Once the CNN has been trained, we can export the weights of the different nodes. This allows us to recreate the training network at any time. An export on the trained CNN has already been created for you under OCR models. We'll now export that model from the Docker container using the following command. So we'll copy the command, put that into here, and we will export it like so. Once that's complete, you can exit the Docker container terminal and kill it using the following command. So exit docker ps to get the ID again. So copy that, and then docker kill container ID. TensorFlow serving will run in a Docker container, so we grab this command, paste that into here, and run it in the terminal, and then we run it. This will start a new hosting of the OCR model that was exported from the AOCR training. We will connect to the model through the API hosted on this address. So brute forcing the admin panel, we're ready for our brute force attack. So they've provided a custom script in the desktop in the brute forcer directory. So we'll go down to here, open up this directory. So this is the script. So makes request, has base 64, encryptor, decryptor, JSON. It's using Beautiful Soup to actually access the web page. Username. So we're going to brute force the passwords, and then it looked like it was going to use website model. Where's that being used in here? And the right here is making a request to the models page and sending data for it to make a prediction. Seems kind of straightforward. So let's run it. So in this directory, we'll just open up the terminal, and then we will run python3 bruteforce.py. So we'll let it run in the background. So in conclusion, in this task we have shown how machine learning can be used for red teaming purposes. We have also demonstrated how we can create custom scripts to perform tasks such as brute forcing, the authentication of a web application. All we need is a spark of creativity. While we could have taken a pre-trained model such as Tesseract OCR, it wouldn't have been nearly as accurate as one trained specifically for the task at hand. This is true for most machine learning applications. While generic models will work to some degree, it's often better to train a new model for the specific task we're tackling. Now that you've had a taste of what is possible, the sky's the limit. So has it... Yep, so it's found the password. So let's go back to the page here. And the username is admin. Password is really not gonna guess this. And then we need to enter the CAPTCHA, which looks like 37720, and then sign in. And we've got the flag here, so let's copy this, and we will grab it from here, and we paste it here. And let's go, what is the password that's generated? Really not gonna guess this. Really not gonna guess this. Okay, now let's go from top to bottom. What key process of training a neural network is taken care of by using a CNN? That is feature extraction. What is the name of the process used in the CNN to extract the features? I think that is convolution. What is the name of the process used to reduce the features down? That is pooling. And what off-the-shelf CNN did we use to train a CAPTCHA cracking OCR model? We used attention OCR. So that is day 16 of Advent of Cyber 2023 completed. If you like this video, make sure to like and subscribe so you can watch me complete the rest of these challenges.